In this video, we're going to learn about spring potential energy. So first off, spring forces are conservative. And let's recall what that means here. Work done by conservative forces are independent of the path. So let's just say that we have an object of some mass m, and it's attached to a spring, and it's starting out at its equilibrium position. So we'll call this x equilibrium. This is the position that the spring and object will be at when the spring is not stretched or compressed. And so we're going to set that as x equals 0. If we were to stretch the spring out by pulling the spring and the object to the right, the spring would be pulling back on the object with a force to the left. So this is the direction of our spring force, and the displacement is to the right. So that is x. And so what we can see here before we do any kind of calculations is we can see that the work done by the spring in doing that is going to be negative because the directions are opposite. In this picture, we are compressing the spring, and if we do that, the force that the spring applies is now to the right, and the displacement then is going to be to the left. So again, what we can see here is that spring force is opposite of the displacement. And that's where we came up with the equation spring force is negative of k times x. It's always opposite. The spring force direction is always opposite of your displacement from equilibrium. So what we're going to do from here is figure out the work done by the spring. We're going to find the work done by the spring called WSP, SP for spring. And we're going to do this graphically first, and then for AP students, we will use calculus to figure out the work done by a spring. So to do this graphically, we need to first graph the force versus x. We're going to graph force versus x, and the reason that we do that is because we know that work is equal to the area under a force versus distance or displacement graph. So let's go ahead and graph the spring force versus displacement. So here's a graph, and we have x on the horizontal axis and force on our vertical axis. And the force that the spring applies looks like a straight line with slope equal to k. Actually negative k, I guess. And the reason that the slope is negative, again, is because spring force is negative kx. So we're just graphing this function. And we're going to pick arbitrary starting and ending points. So let's say we want to find the work done as we go from some position x initial to some position x final. So we need to figure out the area under the curve from that position x initial to x final, and that area is going to be this one here. So we're looking for that area, and to get that area, what you can see is we have a large triangle going from 0 to x final, and then we have this smaller triangle going from 0 to x initial. And so to get that area, what we can do is find the area of the big triangle and subtract the area of the small triangle, where the small triangle is right here. And that'll give us the area that we actually want to get work. So work done by the spring is going to equal area of the big triangle, which is going to be 1/2 times x final is the base, right? The base goes from 0 all the way to x final for that big triangle, and then times the height of that triangle, which is equal to whatever the force is at that point. So we'll just write down F spring, and we want F spring at x final. Okay, and then the area for the smaller triangle is going to be 1/2 the base of the small triangle, which is x initial, times whatever the spring force is at position x initial. And then what we can do is replace, we can write this as 1/2 x final, and the spring force at x final is going to be equal to negative k x final. And then same thing for the smaller triangle, we'll have 1/2 x initial, and the spring force at position x initial is negative k x initial. And what we can do is square those positions. So we can write this out as negative 1/2 k x final squared minus 1/2, well, actually we have two negatives here, so we can write this as plus 1/2 k x initial squared. And the last thing that we'll do here is factor out a negative 1/2 k, and so we can write out the spring, the work done by the spring as negative 1/2 k times x final squared minus x initial squared. So since this is a conservative force, what we're going to do is define the change in spring potential energy as the negative of the work done by the spring, and in this case that's going to be equal to 1/2 k x final squared minus x initial squared. For AP, the equation sheet tells you that spring potential energy is 1/2 k x squared. So this is given on the equation sheet. So now that we know the change in spring potential for a spring, we can write our conservation of energy equation to include that. So conservation of energy says E initial, the initial energy of the system, plus the work done is going to equal the final energy of the system. And initial energy of the system is potential plus kinetic initial plus work equals potential final plus kinetic final. And now this potential energy here could be made up of both spring potential energy and gravitational potential energy. And so next what we're going to do is find the work done by the spring using calculus. And this is really only for AP physics. So if you are in honors physics, then you can move on to the next video. So we're going to find the work done by the spring using calculus. And we know that work is equal to integral of force dotted with dx. We're going to use the limits initial position x up to final position x. And what we're going to do here is go ahead and write this out in terms of our spring force. So this is integral x initial to x final. This is spring force times dx times the cosine of theta, where theta is the angle between the spring force and dx. If we look back up here at our picture, let's say this picture right here, as we're going from our equilibrium position or some initial position to our final position, what we can see is that the spring force is opposite of the displacement. So we're going to use the angle of 180 degrees for that. And so if we do that, then cosine of 180 is going to be -1. And so we can write this out as x initial to x final. And the spring force is going to be kx dx. And again, cosine of theta became -1, so we'll just put a negative out front. And so now we just need to do this integral here. Integral of negative kx is going to be equal to negative kx squared divided by 2. And we evaluate that from initial to final position. And if we do that, we're going to have -1/2 k times the final position, and we have to square that, minus the initial position, square that. And this is exactly what we found by taking the area under the curve.